So in the last video, we defined Liapunov exponents and used them to measure this idea of sensitive dependence on initial conditions. We gave a formal definition of what's to be meant by sensitive dependence. It was this delta epsilon definition, where we say if we have some distance delta that we care about, no matter what distance epsilon we start out with, there exists some point that's within that distance that after some amount of time diverges. Let's draw this out to make it a little bit more clear. So let's see. Let's give an illustration. And I'm not going to draw this on the real line. I'm going to draw this in R2 just to make the illustration a little bit easier to draw. So let's suppose we have some point x naught, and we have some other point, let's call it y naught, that starts out close. Well, then you have some trajectory that x naught goes on each of your points. So maybe that goes there, and then there, and then there, and then there, and so on. Okay? And our point y naught, the trajectory of that, maybe it starts out and it still remains relatively close. But after some amount of time, it diverges. And so trajectories that start near x naught don't stay near trajectories, don't stay near each other. Right? So even if you start off even just a tiny distance away from each other, it matters a lot because you don't actually stay together, and so you diverge over time. And we wanted to measure this. And so one way of measuring this is just to ask, well, how far apart are two different trajectories that start out near each other going to be after t steps? And that's precisely what this delta of epsilon t is measuring here. And we used a very simple example where each time we're just doubling the value of x. And we actually have an unstable equilibrium at x naught equal to 0. And so, given that we have this unstable equilibrium at x not equal to 0, we expect that things to go away from 0 exponentially fast. And so, we can quantify that by just substituting things in. And so, obviously, everything doubles. And so, the distance is also going to double over time. So, you start out with some distance epsilon, and these quantities here determine how fast the two trajectories diverge. And obviously, in this case, this is easy because one of our trajectories is just the equilibrium, which stays in place. And so we just have to measure how far the other trajectory moves away from 0. The two trajectories diverge. And when we do that, we find that for this very simple example, well, there's a linear dependence on epsilon and an exponential dependence on t, and that is precisely the sort of thing we're trying to measure. So, like, as time gets longer and longer, how quickly does everything move away? So, we gave a potential definition of a Liapunov exponent by just saying, okay, well, let's just measure as time gets big and epsilon gets small, how quickly does this diverge? And so we wrote it in list format to match the format of this solution here, up at the top. And then, to make that a bit more precise, what we did is we took limits as epsilon approaches 0, and then we end up getting the list derivative, which is nice. And you also get, as t goes to infinity, well, that doesn't factor out as nicely, so instead we just keep it as a limit in our definition. So once we've done that, we can actually define something instead of, like, we sort of had a heuristic idea of what we meant by these limits as t goes to infinity and as epsilon goes to 0. And one nice thing to do is just to define our Liapunov exponent as that limit. So that is our definition 2.8 here. And you'll note that we sometimes have that the Liapunov exponent doesn't actually depend on the initial condition. So normally in our definition, it depends on what our x naught is, right? So it depends on what trajectory, some other trajectory close to it, etc. If lambda of x naught is independent of x naught, that is, it doesn't matter where you start, you still have the same sort of weird exponential dependence on how long it's been since you've started a trajectory close to your initial starting point, then you can just refer to it as a single Liapunov exponent of the function. And this is, I gave an aside that it turns out this Liapunov exponent is related to whether our equilibria are stable or unstable. So note that it's a more general definition because you don't have to be at an equilibrium in order to talk about stability or instability. Instead, you can talk about the Liapunov exponent at any point. But when you do have an equilibrium, one of the things you can note is that stable equilibria have negative Liapunov exponents because you're getting exponentially, and unstable equilibria have positive Liapunov exponents. Let's give an example of that. So, example. Actually, let me say locally asymptotically stable, which is most of the stability that we've been talking about in this class, but let me just make that explicit. So let's let x sub t plus 1 be equal to x sub t plus x sub t squared over 2. Well, an x bar is equal to 0 and 1 are the equilibria. And this is pretty easy to verify. So you plug in 0, you get 0 again. You plug in 1, you get 1 again. And so now let's compute the Liapunov exponents of the equilibria. Compute Liapunov exponents at the equilibria. Okay, so what's our function f of x? F of x is equal to x plus x squared over 2, which means that f prime of x is equal to 1/2 plus x. So then f prime of 0 is equal to 1/2, and f prime of 1 is equal to 3/2. And so note, of course, that our 0 equilibrium is then stable because by the first derivative test, and our 1 equilibrium is unstable since the absolute value is greater than 1, also by our first derivative test. Well, then we can compute the Liapunov exponents at 0 and 1 respectively. So this is just the limit as t goes to infinity of 1 over t times the sum from k equals 0 to t minus 1 of, well, what is it of? What we want is f prime of xk. But we know that these are equilibria, so xk is just always equal to 0. So this is just the sum of the natural logarithm of f prime of 0. And so you have t copies of this, and so this, the t's all cancel out, and the summations all cancel out. So this is just equal to the natural log of 1/2, which is equal to minus the natural log of 2, which is less than 0. Ultimately, we can do the same thing for the Liapunov exponent of 1. So that's the limit as t goes to infinity of 1 over t, the sum from k equals 0 to t minus 1, of the natural log of f prime of 1, which is 3/2, which is equal to the natural log of 3/2, which is equal to the natural log of 3 minus the natural log of 2, which is greater than 0. Okay, and so it turns out in this particular case, our statement was actually true. So our stable equilibria had a negative Liapunov exponent, and our unstable equilibrium had a positive Liapunov exponent, because for the stable equilibrium, everything, for the locally asymptotically stable local equilibrium, everything was getting closer. And so the negative Liapunov exponent sort of talks about this exponential closeness. Whereas in the opposite case, when the exponent was positive, well, then you go away exponentially quickly. Okay. So in practice, you would approximate this with a computer, and you'll note that it's one important thing is that given any trajectory, the Liapunov exponent of the first step on the trajectory is the same as the Liapunov exponent on the j step of the trajectory, and this is pretty easy to see by our limit, right? So note that the limit as t goes to infinity of 1 over t times the sum from k equals 0 to t minus 1, natural log of f prime of k. Well, you have infinite different things, right? So you're adding together an infinite number of things as that goes to, and then dividing out. And so even if you start at a later point, you still have an infinite number of things there, and so the finite things in the initial part don't actually matter, and so those all fall out. And so you can do your summation that way. And often in practice, it's nice to do this after some number of steps because then that helps things converge a little bit faster. And so if you're writing a computer program to compute Liapunov exponents, this is what you would do instead, or one of the things you might want to do. And lastly, these concepts are generalizable to systems of equations. We're not going to spend too much time on that, but the basic idea is that when you deal with systems of equations, then you have to use the Jacobian matrix and the eigenvalues and the spectral radius rather than just the value itself. So that gets a little bit more complicated, and we're not going to spend too much time on that in this class. But it's important for you to know because chaos is actually a feature of systems of difference equations in addition to just like a single first order difference equation. I think that's about all for these examples, and hopefully that sort of helped illustrate a little bit what the sensitive dependence on the initial conditions and the Liapunov exponents are.